and welcome to the Chemistry Chapter 13 test review. The first type of problem we have is to calculate the amount of heat in joules required to raise the temperature of 200 grams of water from 20 degrees Celsius to 50 degrees Celsius. The specific heat of water is 4.18 joules per gram per degree Celsius. The first step in any problem is to write down our given information. So in this problem, we are given 200 grams of water, the mass. We are given the specific heat, which is 4.18 joules per gram per degree Celsius. Our initial temperature is 20 degrees, and our final temperature is 50 degrees Celsius. The difference in temperature in this case would be at 30 degrees Celsius. The next step is to determine which equation we need in order to solve this problem. Since we want to know the heat, we're going to use the heat equation. So Q is heat, and heat is equal to the mass times the specific heat times the change in temperature. So Q tells us how much heat we have to add in order to raise the temperature of this mass by that many degrees, or the temperature change. So next step, we plug in our given. So 200 times 4.18 times the change in temperature, which was 30. When we multiply those together, we get a value of 25,080 joules. Next, we're going to calculate delta H formation, which is the enthalpy of the reaction, using the values below, and then we're going to tell whether the reaction is endothermic or exothermic. So, let's get started. First, we need a balanced equation, and in this case, we have 2 sodium bicarbonate that is decomposing into sodium carbonate plus water and carbon dioxide. The first step is to find our values. The values are given in the problem, so we're going to multiply how many moles we have of each, which is your coefficient, So the coefficient times the value. For sodium bicarbonate, it is a negative 950.8, which is given in your problem. And we are going to sum each side and get a sum of the enthalpy for each side of the reaction. So we will get a sum of the enthalpy for the reactant side, and we'll get a sum of the enthalpy for the product side. So as we go through, we're going to now plug in the values for our product side. So we have a negative 1130.9 for sodium carbonate, we have a negative 241.8 for water, and we have a negative 393.5 for carbon dioxide. So our next step is to sum each side. This little sigma symbol stands for the summation of a side, or summation of the reactant. So when we multiply 2 times a negative 950.8, we get a negative 1901.6 for the reactant summation. We go to the product side, and now since we have no coefficients, we don't have to multiply by a coefficient, so it's just the value. So a negative 1130.9 plus a negative 241.8 plus a negative 393.5 would give us a summation. We add those together and we get a negative 1766.2. After we sum both sides and get our summation, the next step is to calculate the enthalpy of formation. To do that, we're going to take the summation of the products that we got, and then we're going to subtract the summation of the reactant. So when we do that, we're going to put our negative 1766.2, subtract from that a negative 1901.6, and when we do that, we get a positive 135.4. That is our delta H of formation. The next step is to decide whether the reaction is endothermic or exothermic. Since we have a positive delta H, the reaction would be considered endothermic. If our delta H of formation would have been a negative number, then we would have had an exothermic reaction. For For this problem, we're going to calculate the entropy of the formation. So entropy for the reaction, we're also going to use the values that were given, and we're going to tell if the reaction is increasing or decreasing in entropy. So we're going to use our reaction that was given in the problem before, which is 2 sodium bicarbonate decomposing into sodium carbonate plus water plus carbon dioxide. The next step is to plug in our values and get a summation of each side. So in this case, again, we're going to multiply by 2 since we have 2 sodium bicarbonate. So 2 times 101.7 will give us the summation of our reactant side. Then we're going to add together the summation of the product side. So sodium carbonate is 135. We're going to add to that water, which is 188.8, and to that we're going to add carbon dioxide, which is 213.8. When we do that, we get the summation of our product and the summation of our reactant. So 2 times 101.7 would give us 203.4 for our reactant summation. Our product summation would be 537.6. Again, like we did in the previous problem, we are going to subtract our reactant summation from our product summation to give us our delta S formation, or our change in entropy of this reaction. So we're going to take our product, 537.6, then we're going to subtract from that the summation of our reactant, which was 203.4. When we do that, we get a change in entropy of 334.2. Since this is a positive number, this tells us that this reaction is increasing in entropy or increasing in disorder. When you look at the equation and you look at the state of each of the compounds, you notice that you're going from a solid, and this solid is breaking apart into 3 different pieces. You see that 3 is more disorderly than 2 pieces. Also, you see that you're going from a solid state, which is orderly, to a solid and 2 gases. So that is more disorderly. So when you do your summation, you expect that it should be a positive number because it should be increasing in disorder. The next type of problem is to calculate delta G, or the Gibbs free energy, for a reaction. The Gibbs free energy tells us whether a reaction is favorable and spontaneous. Delta G is dependent upon the enthalpy, the entropy, and the temperature for which the reaction is occurring. So in this case, our given information, we're going to use the delta H that we calculated from the previous problem, which is 135.4 kilojoules per mole. We're going to use the temperature that we're given, which is 298 Kelvin. We're also going to use the entropy that we calculated, which is 334.2 joules per mole. In these problems, we have to convert delta S into kilojoules because delta H is given in kilojoules. To do this, it's very simple. You move the decimal 3 places to the left, so that would give us 0.3342 kilojoules. The next step is to plug it into our equation. The equation for delta G, to calculate delta G, is you're going to take your delta H value and you're going to subtract from that the product of the temperature and the delta S value. So when we plug this in, we have 135.4, and we're going to subtract from that 298 times 0.3342 kilojoules per mole. When we do this, we get a positive 35.8 kilojoules. Since our delta G is positive, we would know the reaction is not favorable or spontaneous. The next type of problem is to calculate delta G, and this time it's at 0 degrees Celsius. For this reaction, we're going to tell again if it's favorable at this temperature. So we're going to use our given information again, our delta H of 135.4 kilojoules per mole. This time our temperature is given to us in Celsius. In order to do these problems, we have to convert it to Kelvin. To convert the Celsius temperature, as you recall, you're going to add to that 273. So 0 plus 273 would give us a Kelvin temperature of 273 Kelvin. And our delta S was 334.2. Again, we are going to convert that to kilojoules, so we'll move the decimal 3 places to the left and get 0.3342 kilojoules. we plug it into our equation. So 135.4 kilojoules per mole. Then we're going to subtract from that 273 times 0.3342. When we do this, we get a value of 44.16 kilojoules. Again, the reaction is a positive number. If delta G is a positive number, the reaction is not favorable or spontaneous. In order for a reaction to be spontaneous or favorable, delta G is a negative number. I hope you enjoyed this video, and I hope it's helpful to you. If you have questions or problems, as you know, give me a call, contact me, and I will help. Thank you.